All right. Now, welcome to the third and final part in our pre-circuits fundamentals. Very long to write this. Number 3. Okay, and so in this video, what I want to do is talk about when you have circuits that have more than one resistor. So if I have more than one resistor, how do I deal with that? Right? Say if I had, switch colors here, a voltage source. So let's say it's 1 volt, but then instead of having one resistor, I also have another one here, right? So I know Ohm's law, right? V is equal to current times the resistance. But then, well, what is the resistance? Do I deal with them separately, or is there some way that I can combine these, right? And so this is a problem. What happens when I have resistors in series? So what do I do with series resistance, right? And then there's another problem, right? Say I have a current source that's maybe also sending 1 amp into one resistor, but then right here at this node we connect another resistor across the first resistor, right? And I can actually label resistor 1, resistor 2. Sorry if that's small. Resistor 1, resistor 2. Now, okay, well, also with Ohm's law before, right, if I rewrote what I've written here, the current is equal to the voltage divided by the resistance, right? Because what happens if I want to find the currents running into these resistors? Well, I knew that I could just take a voltage and divide it, or I could, find some other piece of information first and then kind of work around. But now, how do these resistances deal with a singular current source, or from this current source do we deal with multiple resistances? And this, right, is the problem with what do I do with parallel resistance, right? So there's two things. We can have resistors in series, or we can have them in parallel. There are two other things that resistors can be in some configuration, Y and delta, though we're not going to talk about that. It's not very important for now. Right, and so how do we deal with these? So one approach, one popular approach is to find the equivalent resistance. Right, finding the equivalent. And we would say this equivalent resistance would be Req, where some circuit where you have some complicated mess that we'll put inside this box, right? Some complicated mess that we don't necessarily know what it is. There's a way where you could just make that one singular load, right, that this source is dealing with, the equivalent resistance Req, and then you can characterize that with Ohm's law, right, in this way. So if we can just find, instead of dealing with a bunch of different resistances, one singular equivalent resistance, then we can simplify problems that we deal with. And that is just one approach that's pretty useful. So in order to find the equivalent resistance, we're going to want to step back and talk about resistance by itself. So resistance R, we were talking about in the Ohm's law video part 1, that it's this rho parameter times L over A, where rho is the resistivity of the material we're dealing with, of our material, right? And this is in units of ohms per meter, or no, I think it's ohm meters. Putting another ohm. in ohm meters. And yes, that would make sense because we'll see dimensionally how this works out. L is the length of our resistor, and A is the cross-sectional area of our resistor. And then units on length would be meters, and then units of area would be meters squared, right? And so if we wrote that over here, if we looked at the dimensions specifically, resistance would be, so rho is rho meters, so, or ohm meters, sorry, and then length is meters, and then area is meters squared, right? So numerator, you get meters squared, and we have cancellation. So that, boom, boom. And then you're just left that resistance is in ohms, right? And that's how Georg wanted it. That's how we defined it. Okay, and then so let's set up a picture. So in our case, you have, could be a cylinder, typically cylinders, where the cylinder has a dimension that's the length, and this, in this case, circle has a area that I guess we'll just label as that. And then whatever material this is, material, from that we would get what rho is from the resistivity. And fundamentally, really, it's easier to think about. My professor in semiconductors likes to say that it's a randomization of movement. Once we assume for the most part, even though it's not true, but we assume for the most part in beginning circuit analysis that wires are superconducting just to ease calculations, because every wire in reality does have resistance, just because materials, depending on the material you make something out of, that will have resistance because every material has a resistivity. If we dealt with circuits and we treated every wire also as a resistor, it would complicate things greatly. So in this case, the only things with resistance will be specifically labeled, and we won't deal with conductors like that. But electrons should be freely moving through our conductors, but when they hit resistances, there is some amount of resistivity, as in there's some amount of impeding, some kind of impeding medium that prevents electrons from moving from A to B quickly. And so by preventing their movement, you're adding randomization potentially in where they're going, and then that can be seen as resistance because charges are not moving as quickly. So your current changes. Okay. So now from here, from this equation, notice that the resistance minus the scaling factor, ultimately that rho is, the resistance is a function of your resistor's geometry, right? It's directly proportional to length. And I'll write that maybe here. Resistance is directly proportional to the length, and resistance is inversely proportional to area. So if we increase the length of our resistor, then we're going to get an increased resistance, which could be good or bad. And on the other side, if we have a parallel, I'm actually skipping ahead here, but if we have a resistor and we increase its area because of the inverse proportionality, then our resistance is going to decrease. Okay, and I did get ahead of myself in a second by kind of blurting out parallel. However, these two variables, these two parameters changing our resistor's geometry can exactly tell us what's going on when we are doing resistances in series and parallel. So these are the key, right? These are the key to series and parallel resistors. So thinking about, right, if we stretch our resistors, we're increasing resistance, directly proportional. If we're fattening up the resistors, stacking them in some way to increase their area, then we're decreasing the resistance. And I guess fundamentally too, we should think about just from here, right? If we're increasing the length, so we have a resistor, and just if we think now we've stretched this resistor, now if we then sent an electron, that's impossible to see. No one will be able to see that. That's fine. We can go here. If we have an electron going through, it has a shorter distance to travel through the resistor. In this sense, if we have our electron here, right, there's a longer distance it has to flow through. The longer distance really being the elongation of time it takes for it to flow through, because the resistor is one longer. Just because it's longer, actually. Because Okay. So then now, if we're then thinking about a resistor in parallel, right? If we looked at a resistor here, right, and then we looked at a resistor here, right, it would be harder for electrons to fit into this resistor compared to this resistor. More electrons can fly through at any moment, right? And so in this case, we want to think about what happens when we're setting up these. Actually, I'm going to need to increase the size of this. So we need to see what happens when we start placing them in series and when they're placing them in parallel. So let's start with series first. Placing resistors in series. Okay, so now if we place a resistor in series, we have one resistor, right? This is what we originally had, some resistance R. What if instead I place R, and then another resistance R, and then another resistance R? Visually, it looks like I just increased the length of this circuit, right? So from here to here, right, this has to be a longer length than this, right? By stringing along resistances, you're increasing the time. You're increasing the time an electron is flowing through something, right? And if you're thinking the distance formula, a distance is equal to a rate times a time. Our electron, let's just assume it's moving at a constant rate through this resistor, right? We've increased time, and so therefore we're going to increase, right? We're going to increase the distance or the length that this electron is flowing through our resistor. So what we do when we set series resistors in series, we end up increasing the effective length. So we've increased the effective length of the resistor. And, right, looking at our formula, resistance is equal to rho L over A. And so if we increase, let's get a different color to make it clear. If we're increasing, chose like the worst color to make it clear. If we increase length, we increase resistance, right? So that's where we're going to keep that for now, right? So intuitively, we're thinking we're increasing length, so we're increasing resistance by placing multiple resistances along each other in a chain. Okay. Now, resistors in parallel. Okay. So, right, original picture, and I'm actually going to draw this top down, we have a resistor. But we could potentially have multiple resistors all alongside each other. And let me say, the resistors here are sharing the same nodes. If something is in parallel, it means that they share the same two connections / nodes, right? Last video talking about Kirchhoff voltage and current law, which I misspelled. Looking at junctions, a junction is considered a node, and those are just points of connection between different elements or branches in your circuit. And so if you have any circuit device in your layout and they're connected, right, if they're sharing two connection points, and visually it can be hard to deduce what's in parallel sometimes, as long as you can say and show that see that they're both connected and sharing the same two nodes, then they're in parallel. Okay, and then let me put little resistance labels, just R's. We could say that they're all the same. They might not be, but they could. So if we're looking here and we want to think about, again, how an electron is looking at, instead of moving through one resistor, it has multiple choices to make. Right, let's think about if you were going to an amusement park. Okay, so here we are at the amusement park. And you're gonna walk inside, you have your ticket, but there's only one entrance, right? This is the only entrance you have to get inside. And someone's checking your ticket in there, and you're standing right here. But, right, there's also, let's use purple. There's a bunch of other people also trying to get into the park at the same time. They're all ticket holders. They're eager to get inside, right? And there's only one door to walk in through, so now you have to wait for potentially every single person to individually walk through. It feels like it takes forever, right? But you could have multiple now of these entrances right into your amusement park. And now it's not so bad because you could have this guy coming in here, them going there, them going this one, here and here. And, not all of them have the same amount of people. Some might have more, some might have less. But you have more doors to walk into, so more people can enter the amusement park at any time, right? And this is exactly what is going on when we're thinking about resistances in parallel. So let me draw. So you have your circuit here, right? You have your resistors placed in your configuration here, and we can draw a little bit more three-dimensionally. So we have our resistors, which I'm making tubes for now, right? And they're all connected via this superconducting wire in the front and in the back, right? And if you're an electron, right, now you're making your choice. But, in a circuit, there are insane amount of electrons trying to flow through your circuit at any time. But now, because you have all of these extra resistors, instead of trying to just flow through one resistor, which would take a while to deal with all of your electrons, now these electrons have, in this case, 3 different paths to take, right? Instead of one opening, there are now 3 openings to flow through. And so if you added up all of the areas per se, instead of having one area for the first case, for the second case, you now have 3 areas to flow through. So when you're connecting resistances in parallel, how did I word it in the first one? Increased effective length. So now for this parallel, you have increased effective area of the resistors. So there we go. We have increased the effective area of the resistors. But just from here, that doesn't necessarily mean that we've increased the resistance of the resistor, right? Because if we look back at our equation, resistance is rho L over A. So we've increased the area, right? But we've made it easier. We've made it easier for electrons to flow through the resistors. And that follows in this equation, right? Because if resistance is proportional, inversely proportional to area, right? Then when we increase area, we make it easier for electrons to flow through. We get a decreased resistance. So there we go. Those are nice explanations. Now what we want to do is think, okay, that's interesting, but how then do we take mathematically and describe the equivalent resistance that we have now, right? Because you're not always going to want to analyze a circuit and then say, okay, well now resistance is rho L over A. You're not worried about that per se when you're designing your circuit, right? You want to see, how am I playing with the resistances in a more abstract sense at a higher level, right? And then I need to increase the size again. Okay. So, right, what we can do, and this is why last video I talked about KVL and KCL, we can kind of derive the series equivalent resistance and the parallel equivalent resistance. EG. No, EQ. Okay. So let's just have a general case. So we have a voltage source and we have 3 resistors in series. These are pretty horrible resistors. Okay. Not much better, but it's okay. All right, so this is R1, this is R2, and this is R3. And then we're going to say that this is just a voltage V. So what we want to do, right, our end goal is figure out how can we condense this into a singular resistor knowing what we know now. So R equivalent. We want to figure out how to take R1, 2, and 3 and make it R equivalent. Well, okay. So when we look at this circuit, I have a voltage source. I have a resistive load being put against this voltage source. And by Ohm's law, I'm going to have some current I flowing through, right? And so, okay, if I think about conservation of charge, if I have just one loop that I can work through, the current flowing through this resistor should be the exact same current that flows through this resistor, and also the voltage source, right? Because there's nowhere else for it to go. It has to stay contained within this conductive loop. And so all of these resistors have the same current. And that's actually a nice note to make off to the side. Series elements share the same current. So that will be a useful thing that will definitely be used when we analyze circuits later. Okay, so what we want to do, let's flex our use of KVL that we learned last time. So KVL, right? So let's label, okay, well, all of these resistors, let me actually erase this I right here. It's going to be harder to see what I was going to say, where we have I flowing through here. So across R1, we know there should be a positive voltage from here to here because current's flowing into this resistor from top down. So we'll have a positive to negative voltage drop. And we're just going to say it's VR1. Because there's current flowing through, by Ohm's law, current times resistance is voltage. Same thing across R2, we have VR2. And across R3, we have VR3. So from here, we can use KVL, right? Conservation of energy all throughout my loop. If I start from the beginning, go through the loop, get to the end, all of the voltages have to add and equal 0. Can't be creating or destroying any energy here. So if we start and follow the path of the current, which is pretty typical, pretty conventional, going through the direction the current's going, we'll go up into the negative terminal of the V and get minus V. Come around, we would go into the positive terminal of VR1, so plus VR1, into the positive terminal of VR2, plus VR2, and then same through resistance 3, plus VR3, and that all equals 0. Okay, now what we can do, right, is use Ohm's law to rewrite what VR1, VR2, and VR3 are. Because, via Ohm's law, voltage is current times resistance, if we know that there's a current I flowing through each resistor, well, then their voltage should then be, because going through the passive sign convention, I times that resistance. Okay. So then this can be rewritten as negative V plus I times R1 plus I times R2 plus I times R3, and that's all still equaling 0. And then what we can do is we can solve for I right away. What we can do is add voltage on both sides, and then we can factor out an I. Right, we'll see this. If we factor out an I on this side, right, each resistance has I multiplied onto it, so we can say I is then times R1 plus R2 plus R3. That will equal V. And notice what we have here. Right, this looks a lot like something that we know. It looks a lot like Ohm's law, where I have voltage is equal to current times this right here, which is our equivalent resistance. Okay? And so we get right here that our equivalent resistance, Req, is equal to R1 plus R2 plus R3, right? So the sum of the resistances in series, okay? This is huge. So generally, to find Req for series resistors, that's going to equal the sum of, right, all of your resistors in series. Okay, so that's nice. And this follows, right? Because if we string these resistors together, increasing the effective length, we're going to be increasing resistance. And so we'll see larger and larger values as if we're adding the resistances together, right? Which is what's going on. There we go. So now we know how to deal with series resistances. So let's talk about parallel. And then we'll be done. Parallel resistors. So in this case, I believe I want to also, I think I want to use a current source here. So if I have a current source I that I'm putting into 3 resistors in parallel, R1, R2, and R3. What would be nice, right? So the last one we found the current. So it would be nice if I could find the voltage, and maybe that will tell me what's going on with these resistors. find the voltage. Where the voltage, I'll just call that V, that is across everything in this circuit. So before I made the connection that in series, everything has the same current. So here, what's nice is that parallel elements all have the same voltage across them. And this is actually something that really helped me out when I started, was accepting and noticing everything in parallel has the same voltage, everything in series has the same current, right? So if we can find V, well, that's the current or the voltage that's across all of these resistors, right? And consequently, also, if we have a current I flowing through all of these and I want to know their voltages, well, I'm going to need to know the currents flowing through all of these. I'll say that's I1, I2, and I3. This picture's getting pretty cluttered. But if I know all of the currents flowing through our resistors by Ohm's law, V is equal to IR, right? Those multiplied together give me the voltage, and that's what I want to find. Okay, so what we can do is that here we're looking at a large node, but this is all the same node. So even though it's not like a clean junction like this, anything where they're connected, even by a distance like this, right? They're all still this is a single node, and what we can do is apply Kirchhoff's current law and look that all of the currents entering must equal the sum of all the currents, right, leaving that node. And then we can start deducing things about our equivalent resistance here, right? And I will, before I start working, say our goal is to figure out, right, if I can find some equivalent resistance. Okay, let's get cracking. So, right, if I do a KCL, then if I'm looking at this node, our current source I is entering our node. It's supplying current to this node. So then on the left-hand side of the equation, right, and actually let me write sum of the currents in equal to the sum of the currents out. And I might not ever write things the same thing or the exact same way twice, so bear with me. I think I said something different with in and out the other video. But okay, current entering is I. That's going to equal all of the currents leaving, which, as we can see from this node, are I1, I2, and I3. And notice that I kind of arbitrarily labeled those currents. This is another thing with circuit analysis. I could have labeled these currents going the other way, but then I would have to deal with the passive sign convention, and all that would change is that the current value that you would get would be the opposite sign, and you would just interpret that in the way that you're looking at your graph, or not your graph, but your circuit diagram. But things like that will come up in other videos, and so we'll be able to see that in due time. So, but now we have a expression relating all of our currents together, right? Okay, we made a major mistake with the algebra, so we're cutting. We are editing this. Okay, so now we can use Ohm's law to rewrite what these resistances are, right? And let's, right, V is equal to IR, right? So then the current is equal to the voltage divided by the resistance. Okay, so then what I can say is I is equal to I1, so looking passive sign convention, I1 enters V, so then from the top, so plus to minus, positive Ohm's law, so then I1 is equal to V over R1, right? And noticing that, again, these are in parallel, so all of them have the same voltage across them. So then I2 is going to be V over R2, and I3 is V over R3, or I3 is V over R3. And now all of these have the same voltage, so we can pull that out as common. So then we have 1 over R1 plus 1 over R2 plus 1 over R3. And then, right, now we want Ohm's law to be V equals I times some scaling factor. So then we'll move and divide this to the other side. And that would be V then is equal to I, the current, times 1, and now this is going to be larger, 1 over R1 plus 1 over R2 plus 1 over R3, right? Here, now, our equivalent resistance, as we identified before, this is REQ. 1 over all of the sums, or the sum of 1 over the resistances, right? So now this is the way that we can find equivalent resistance for parallel. So parallel REQ, where REQ is then going to be the 1 over the sum of all of your parallel resistances, 1 over those, right? There's a lot of 1 overs. And so there we go. Okay. And so, for example, let's say that we had a few resistors in parallel, and we'll show that their equivalent resistance has indeed lowered, like we were talking about earlier with electrons or people trying to enter an amusement park. So, in this, say we have 1 volt, it won't actually matter. Let's just say we have 2 resistors. One is 2 ohms and one is 4 ohms, right? And I want to label these two as resistors in parallel. So what we could say is that the 2 ohms is in parallel with the 4 ohms. This is a way to condense saying that these are in parallel, this symbology where you have 2 parallel lines in between them. So our equivalent resistance, if we use 1 over the sum of 1 over the resistances, then our equivalent resistance would be 1 over 1/2 plus 1 over 1/4, which would be equal to 1 over 1/2 is the same as 2/4, right? 1 over 2, 4, or 2 over 4 plus 1 over 4, which is equal to 1 over 3/4, which is equal to 4/3. If you're dividing by a fraction, it's the same as multiplying by the reciprocal. And so instead of 1 divided by 3/4, 1 times 4/3. So it's 4/3. 4/3 ohms. And so 4/3 ohms would be about equal to 1.333 repeating ohms, right? Which is less than 2 ohms or 4 ohms. So if you're putting these in parallel, right, these two larger resistances in parallel, overall you're going to get a resistance lower than either of those. And you'll always find that to be the case. No matter what, the equivalent resistance from parallels will be less than any single one of those resistors values from or originally, right? And it's absolutely lower than if you put them in series. Okay, and I think now we have all of the knowledge we need to start doing some circuit analysis, right? So just run down equivalent resistance. If they're in series, it's if you sum them together because you're increasing their effective length. And then if you have parallel resistances, that is 1 over the sum of the 1 overs, which is basically increasing their effective area, which is then decreasing the overall resistance. So, all right, there we go.